can start this lecture. This probably is one of the more mathematical heavy lecture. It's unavoidable. Some of other lectures will be similar, but hopefully not many of those will be. And I think this one probably is one of the most mathematical heavy one. It mainly use calculus, some probability and statistics. Anyway, so if you recall the end of last lecture, we talked about autoencoder. We talked about it can be used for generation. Recall what is it for? And okay, there are two things, right? If you just recall, one is encoder, one is a decoder, right? Encoder is for representation, and decoder for generation. We will still continue this view this time. Basically, we will move from autoencoder to variational autoencoder. Essentially, variational autoencoder is built on probability model. So we will talk more about probability model, I think in part 3, when we talk about image generations. And we actually focus more on generation this time. Last time, probably both generation and representation, but more focus on representation, the encoder part. Right now, we shift to the decoder part. And then, yeah, because of the way you involve probability model, it's not just simple intuition, you have a loss function, but now it actually comes from model. So it needs some mathematics. So I don't think it's avoidable. Concerning the topics, so essentially, this is just one topic, right? VAE, variational autoencoder, right? So basically, it's a probability version of autoencoder. Variational is a computational technique, which we'll talk about. So again, if you say what is the key difference, right, with variational versus traditional autoencoder, it's a probability model part, which is and probability model naturally lets you to do the modeling of the distribution over latent space, which we left over from last time. So let's just recall this autoencoder. And at the end of the last lecture, we did talk about using autoencoder for generation, right? So if you recall autoencoder, you have an encoder, you have a decoder. Encoder is for representation, which generate a small dimensional vector. Original vector, say X is in RD. For MNIST, it's a 28 by 28 dimension, right? It's almost 1,000 dimension. Then for Z, it's a lower dimension, say 2, 4, 16, whatever. It's just a small dimensional representation of your original data. And this bottleneck, when you reduce the dimension in your representation, create something which is useful for a lot of tasks. So that's why we reduce the dimension, also called the bottleneck. Now, this one is certainly something which is very useful, right? Representation encoder. Now we talk a little bit about decoder. Decoder we know can be used for generation. And at the end of last lecture, we try to say when we use encoder, decoder to train these two things so that minimize reconstruction error, we can generate other images from this Z in the hidden space, sometimes called the latent space. Z is also called the latent variable. Basically, it's not observed. It's something you create, the representation. It's not observed in original data, right? So called latent. If we know how to generate a Z, then we can use the decoder to generate X, just from or X tilde, whatever, from X, right? So basically, this is that, and this is a picture, more graphical representation about just showing that encoder will reduce your dimension, decoder typically enlarge your dimension, and if you recall, we have a CNN, we have deconvolution, convolution, right? So, but those are more the implementation side. But the mathematical side, what we want to say, we want to learn, we want to generate X from Z. So that's the thing we want to talk about today. To generate new data, recall last time in the out, we first sample latent code. We just generate Z, right? If we can generate Z, then we use decoder to generate X. So that's the workflow which we basically follow for this decoder generation. You can discard the encoder. You just work with the Z, right? So, okay. So now this is a thing. If we want to do this decoder generation, one thing we need is we need to sample from Z first, right? First, we'll get a sample of Z from the Z space, latent space. Then we use a decoder. So the key is, can we have something with Z, right? So this is part motivation, particular motivation for variation autoencoder. Let's recall the key issue, which we already showed at the end of last time. Yeah, standard autoencoder. Division of Z is unknown, unconstrained, because we don't put anything. We already seen the picture. It can be anywhere. Although it looks a little bit like a Gaussian, but that's not exactly the point. It's just say all the mean and the variance are unconstrained. So, so you will see that moved away from zero. You will see that unclear. So if Z is a very complex distribution, that is hard to sample, right? So what do we really want? Basically, a solution, or say, if we want to do the simple generation, why do we constrain Z to be a standard normal distribution? Zero mean as identity as a covariance, which means variance of one along all the directions. If we can achieve that, so we can sample Z just from this standard Gaussian distribution. This is easy to do. And then once we sample the Z, right, we will be able to do that. Now, recall that again, in the standard autoencoder, because Z is unconstrained, random sample, let's say from Gaussian, let's say the very typical sample is 0, right? 0 will be out of distribution. 0 will be the most representative sample from the Gaussian with mean 0 is a mean, right? But it actually considered out of distribution. We see that it generates nothing if we just train a regular autoencoder. If we want to have a nice nice generation, this is not sufficient. Reconstruction for the autoencoder can be fine, but the generation can be poor because of the Z is complex and is typical, very different from the standard normal distribution. So basically, this is, I just recall what in the end of the last lecture, what we covered. So what we can do, right? So one thing we can do is desired probability, again, is normal, right? So one thing we can do, just let's just do intuition, just something you say, oh, if you are aware this is one, then what you can do? There are simple solutions. This is not a VAE, but just a simple, you can say it's a hack or it's a simple method, right? Essentially, we could put a regularization on Z so that it forces a zero mean and identity covariance. Just try to make it so, right? Encourage this. So how do you do that? Z square, right? If you say, oh, z squared, which basically means you want z to be small, usually it will get you where the smallest mean will be 0. So typically it gets you close to 0 mean. And z transpose, this is not entirely covariance. It's just, it's just it doesn't subtract mean, but basically it's just a simple approximation to say, oh, this is identity. This is simple just for illustration. So what do you need? Basically, the point of this, you need some regularization on the latent space. And we could create something. This one is like moment matching. This is very easy to implement. Loss function, right? So if you look at this one, loss function with z latent regularization, right? This particular regularization, this is a mean. This is our original reconstruction error. So mean squared error for whatever y minus your reconstruction. This guy is something, whatever, it's something so-called whitening loss, which basically implement this guy. It just for illustration. I'm not proposing this loss, but just demonstrate that once you have this one, you have desirable property in the latent space. Okay. So you could use random projection if you want to have a larger dimension, whatever. So we don't want to go over that. But basically, let's say in a small dimension, say dimension 2, you just directly implement that. It's feasible. Just using this particular approach. And you can see what it happens, right? This approach matches the lower moments. It doesn't build a probability model. So it's a simple method to achieve desirable effect. In many cases, I mean, if you other, for example, other situations, if you see, oh, I identify a problem in this particular for like a generation, right? Generation, you say, oh, because when I sample is not untypical, therefore I want to fix that. So this kind of thing regarded as a simple fix, right? You can think, what I want to do, let's impose some conditions, let's impose constraints and so on. So later on, we will get a better, more motivated constraints using variational autoencoder. That essentially also get your constraints, but it's a different constraints, which we'll soon get to that. But this one is a simple fix. If you know a little bit of probability, that's what you can do. And here these two scale are different, right? So if you look at this one, if this one is from -2 to 3, maybe I should make it a similar scale, but it just I didn't do that. So basically scale is a little bit, but basically this one is one thing you see that is unlike the distribution we see before, which is shifted far away. The mean is far away from 0. Now it's very close to 0. These two are actually slightly different scaling. So that's why you see that doesn't look. In fact, it's somewhat diagonal. So we can see. This one basically is actual. This one is just a Gaussian approximation, but they are different scales. So, but actually, if you have the right scale, they are looking right. But here you can look at the mean and the covariance, right? Mean is close to 0 now. If you recall the last time, it's maybe, I don't remember, it's 20, 30, whatever, it's a big number. Here is pretty close. This one is not identity because we are not really doing covariance. So if you look at the regularization, so but it's it's close to it's a little bit close to a diagonal. I mean, this one is small, this one is larger, and so on. It's not perfect, but nevertheless, it's better than before. Basically, if you look at these, so if you sample from standard Gaussian, it will get something actually reasonable, which we will see. The point is, this kind of regularization, you could impose getting something close to what you want. Not necessarily perfect, but close to what you want. Here is what it generates, right? So 0 now, because it's 0 is not out of distribution now. It's centered in your distribution, close to your mean. So 0 now actually gets you the roughly standard kind of sample. It's a typical sample, right? If you change a little bit, just draw from the Gaussian, whatever, right? So it will get you a different shape. It's just somehow you get more variations about your sample. So basically, you can see typical sample variations of a sample by drawing from different samples. You do see different samples, right? Yeah, this is mean 0, and there are some other typical samples from Gaussian approximation. But anyway, so this one closer to what we do, what we want. So essentially, all I'm saying here is the point is we need to introduce regularizations into the latent space such that the regularization enforce the latence to be similar to a standard normal distribution so that you can sample from that. Okay, so now let's say VAE, right? So with this background, hopefully we have strong motivations for VAE. Basically, VAE does require your Z from the probability model point of view to be a standard Gaussian. So that's into the model. So they put that into the model. So that's something nice. You could also look at a little bit different ways about looking at these. So instead of mapping X to a single point, the encoder actually become a distribution. Decoder is a distribution, it's always a sampling. But the encoder maps X to a distribution over Z, which is a way of doing so-called variational inference. We will talk about that. But essentially, the implication of this variational implication of you want force distribution encoder instead of deterministic as before now becomes probabilistic, which we will show. Okay. The training explicitly encourage this particular distribution, encoder distribution, right? Goes to be close to 0, to be standard Gaussian. And therefore, eventually you will see that actually comes out like a standard Gaussian. So, so basically, you know, the key result about that is first you have a probability model, which I probably should also mention. But the key difference, if you compare with encoder with a autoencoder, variational autoencoder, you see some randomness, you see some regularization, so that is encouraged, right? You see that actually random of Z, and you eventually it's actually in the Z space, eventually it's look like standard Gaussian. So it will that will be the effect. And this is desirable. So even you think about autoencoder, whatever, right? A lot of people use VAE now. For example, combined with diffusion model. Diffusion do better generation than VAE. But even for representation point of view, if you say I can encode my X to something like a standard normal distribution, from representation point of view, it's also nice because you know the distribution, more controllable representation. So therefore, people actually, not only for the generation purpose, although our motivation here is from generation, but from representation point of view, the current a lot of use of VAE is just say using the encoder of resulting VAE, we have a better representation because it be distributed like a Gaussian, which is considered as a nicer representation. Okay, so this is something which we are doing. Here we want to compare just from a programming point of view, what is the difference of denoising autoencoder and variational autoencoder, which is about where we inject noise, right? In the denoising autoencoder, remember there are also some random if you consider this guy. You first generate noise using the here, right? Then you pass encoder. This one has no noise in there. So once you get here as the input of your encoder, it's a deterministic. In the variational autoencoder, actually noise injected after is here. So it's actually may say you have a Z, which so VAE we keep the input clean, but add noise in the latent space. This is what we look at. You can think about from here to here, right? If you think about the encoder is from X to Z, then it actually requires one of the sampling step. So it's a random. You could also say encoder first generate some distribution parameter, then you sample from this distribution. So this one is the distribution parameter mean and covariance, or variance, yeah, just the diagonal variance. And then this guy sample from here. Then you can say, oh, encoder is deterministic, but Z requires sampling. Okay, either way is fine, but essentially you are injecting noise not here, before the encoder, but after encoder, at the Z. Okay, Z is random. Decoder is also random. So this one is because it's a probability model. So now the loss function, actually, because you have a probability model, now the function is a negative log likelihood. It's always a negative log likelihood for the decoder. Okay, decoder is a negative log out. Encoder is a variational method which is implied from using these. So you first looking at the decoder generation, and you input a strong standard Gaussian here, and you say decoder whatever the probability model, then you use maximum negative log likelihood loss. So that's you finish the decoder design, and then you imply the encoder, which we'll see how that implies. But it implies encoder, which has this form. You have to inject noise here, basically. Training VAE is training of this one. VAE actually your sample according to these. So encoder generating some model parameters, mean and variance, and the decoder. This one is a standard normal. So you just decoder is mean plus noise times the standard this normal distribution, and then you decode, right? So basically this is a latent, and then you decode. So basically this is a probability model just from a training point of view. We will write a training function, then you see that with this encoded what it looks like, then we will have to derive what it is. Right, so this one actually you require some regularization called KL regularization, which will soon come to that when we talk about the variational. Essentially, it's forcing Z to look like a standard normal prior, which what you want. Okay, so that's what it is. VAE regularization on the latent space, right? So basically, if we remember, we mentioned VAE is kind of a regularization on the latent space. First, it changed the latent to be a distribution instead of using encoder. Encoder basically generated these parameters, both mu and sigma square. Sigma is your Gaussian noise. Epsilon is a Gaussian, is standard normal. So this one is a Gaussian. This is a Gaussian with a zero mean, with mu as a mean, sigma as your, sigma is a vector. It's an m-dimensional vector. It's a diagonal vector. It's a diagonal of sigma is your normal distribution. So objective here is basically they say, oh, this is my Z, right? Z I mentioned it's a random. It's this guy. This is your Z minus your X, right? It's similar to the denoising autoencoder inject noise, but it's a different place. Denoising autoencoder inject noise before the encoder. This guy is already after encoder. Encoder gives you the parameter. Unless sigma is 0, it will be random, right? If sigma is 0, it's not random. It's just your encoder. But the encoder not only encode the mean, but also some variation. Here is a key part, which shows that what you want the distribution of this guy be. If you look at that, what do you think? I mean, so you can think about, okay, this is regularization on my mean, on my the standard deviation sigma, right? If you look at that, I think what it should be encourage that too. This one pushing this. For mu, the minimizer, if you look at what is minimizer, mu square, right? It's a 0, which means it favors a mean of 0 here. This guy, if you do a calculation, you can think, what is the minimizer of this guy, right? You can do a calculus. Yeah, and actually it's a 1. Essentially, this one push together this sigma to be 1 on each direction. So this is a diagonal sigma. Each sigma at each direction it favors 1. Favor mu, the mean as 0, favor the standard deviation sigma as 1. And what is that? That means it's like a standard Gaussian, right? Because you are injecting sigma. So this one, if you have 0 mean noise, sigma is 1. This is a standard Gaussian. So basically, for each of these, every of these one, it says it behaves like a standard Gaussian. And this is controlled by this latent regularization, which enforce that, or at least try to encourage that. So this is the effect. And you can write down this loss function easily, which will show the code. I mean, just exactly this loss function. Tau is some parameters which we'll come back to. From the probability model point of view, we can have this one into the probability model. This is a standard reconstruction loss with some noise, except this denoising is a little bit different from the denoising autoencoder. In the sense of denoising autoencoder have noise before, and this one is after, right? And this also is automatic, so there's no model parameter; it's just automatic. And this one encourage latent variable to be standard GOMO. Okay. The question is, how do you derive that? I mean, this one again looks like we said, oh, we can introduce this. This look at heuristics. Just looks like a makes sense if you think about what it actually encouraged to. It does seem to make sense, but then one can say why you have to do this way, right? So this is where the math comes from. At this point, it's not too much math. You just say explain what if you look at this loss function, VAE objective function, which you actually done. But then when you derive that, this is where the math comes in, which is the next few slides, which is actually more mathematical than the previous ones, but we will see, right? This guy, as I mentioned, mean 0. This guy, sigma to be 1, right? So basically, yeah, basically this encode Z to be samples. This is Z sample, right? This guy to be standard normal. So that's what it is. And that eventually you can see that it will have this kind of behavior. It gives you the right behavior once you look at the loss function. Next, we will look at how to derive it. Then we will come up with from how do you try to derive this mathematically. This is coming the next. Mathematical formulation, right? First, it's actually generative model. It's a generative. Basically, they look at the decoder part. Again, VAE started with decoder. Decoder is for the generation, which we talk about. So with decoder part, you start with sampling something from the latent space. Now, for this probability model in the VAE, we assume this latent space is standard normal. So that's what we want anyway. So right when we say, but this is starting point. So we do that. And now let's say, what is my observed image, right? And it looks like, given this normal, you need a probability model, so you have to have adding noise. So this is one part of VAE. They may somehow people argue about that. So whether this is something, but nevertheless, this is something you're adding noise. Usually, when you have an autoencoder, right? You have a decoder. That's your generation. VAE, you have to add another noise, which is a tau. This is where the tau from previous comes from. Yeah, this is a tau, and this is basically model. So model is the first generate this guy. Then when I generate a VAE, generate the original image, I will start with a latent, run the decoder. Decoder gets you the image. We see the decoder code before, right? So you just given latent gets you the image, and then you're adding a small noise. This noise has model tau square with it's a Gaussian, a small Gaussian. Here is the overall probability model, right? So probability model, if you look at that, that is exactly what it actually does. So this probability model is when you have a latent variable model, you have observation X. How do you model that from basically the probability or statistic? This is a very common model. It shows that you integrate out the Z according to the distribution, so-called marginalized Z. Once you do that, then become probability. So essentially, this is a Gaussian. This is your likelihood. Likelihood is another Gaussian. This is a latent variable model with a Gaussian prior and this Gaussian, right? So basically, this is the form of that. This is a Gaussian with this encoding this guy. This is the probability. This Gaussian is a standard normal in m dimension. Okay. So this is basically what it looks like. Any questions so far? Yeah.
So why the
this
top set?
This one?
Why is not decoder with input z plus epsilon?
This one is a z. I mean, this is just defined. Given z, it's this is a definition. Usually, autoencoder will just z. You mean say not inside this one? Because okay, you could do that, but then that will be harder to model. This one has a clean model like this. If a z plus epsilon, then you can call z plus epsilon z instead of z plus epsilon, right? You just call z plus epsilon z, your new z. Then this one, because that's nonlinear, you don't want something here messing up. Yeah. If you say, oh, instead of z plus epsilon, then why do you don't just call z plus epsilon z, your new z? Yeah, basically. Yeah. Okay.
Why not just z? I think you add a epsilon in the output of the encoder.
Yeah, because you have this model. Yeah. When you epsilon, the only reason is they want this model. VAE has to work with the probability model. And if you say tau is 0, this one is deterministic, then somehow it doesn't really work well for the VAE. It's just that formulation, mathematical formulation it becomes singular. Yeah. They work with this particular model and work with maximum likelihood. So this one, you don't want that to be 0, and this one, yeah. So this is actually a drawback of VAE. In practice, you would see there's some blurring effect, but we are not talking about that. We are more talking about how to divide, assuming this is okay. Okay, yeah. I mean, fair enough. You say there are people discussing whether this probability model is good or bad, but that's not the point we are talking about. We are talking, let's say, given this probability model, and with this form, you don't want tau to be 0 because of this. Okay, and then what do you do with that? So what do we do with that? You want to learn the model parameter, right? So now we only have a decoder. Remember, we only have a decoder generator. We don't have an encoder yet. We see this form, right? This is a decoder. You can write this p theta x, which we see before. You use a maximum likelihood. And this guy is the integration of this guy. We mentioned that. And then if you do that, you have this integration. This is the standard normal. This is where we generate x according to z, according to that particular Gaussian model. Tau is now 0 here. That's yeah. So that's the one problem is the following. So if you look at that, I can tell you is think about it. This is a neural net, right? If you say, oh, I have a neural net output, this is a loss function. For specific like a z, I evaluate this is fine. But if you say I generate average over z, right? What is this loss function average? And you have to draw a lot of z. You do this average, and then you integrate out. This is computational not tractable. If you read it, this is your loss function, and then you sample over z. So basically, it says this is not good. We will not be able to handle this. Okay, the integration is not computationally trackable because there are some nonlinear. So what is easy to do, right? You think about that. If this decoder is linear, right, then you can integrate out with the model parameter. That's still complicated, by the way, because they are involved covariant matrices or whatever. But nevertheless, you do have a closed form. But for the neural net, as we do, like CNN, whatever, there's no way you can do this, basically, because of this nonlinearity here. Okay, so so the point is it's not going to happen. right? So then what we can do, right? What we can do is we approximate by tractable, so-called now coming from a variational, this is where variational comes in. A variational method will introduce encoder to this. Now this only decoder only model. Decoder only variational method get you the encoder, okay? So-called variational lower bound. And the trapdoor lower bound refer to so-called evidence lower bound, or short, you can see elbow is it's a common terminology. You can read whatever there. But basically, that's what we will try to introduce. This is where the mathematical part, okay, when we do the elbow. Okay, so now we are hopefully try to do. Here is the elbow. We will not give the full derivation, but we just give the results, and you can read that. That's fine. This guy, it's a lower bound, so it's an approximation. Because we are usually this is a log likelihood, right? Usually loss is a negative log likelihood. It's selective. So when you have an elbow, it will become negative elbow. Negative elbow will be upper bound of your loss because negative. This is a lower bound of likelihood. Upper bound negative log elbow will be the upper bound of a negative log likelihood. So we look at the negative elbow, we look at the upper bound. So minimize. Basically, yeah, you might maximize this one, you maximize the lower bound. So that's essentially replace this by a lower bound. Yeah, essentially, yeah, that's what it is. For any Q, you can get. This is the definition of KL, right? So basically, KL is a standard notation. You just have these. Eventually, we will look at the KL for Gaussians, so we can have a closed form. We will soon get there. But basically, you know, it's a this is elbow is always this. So if you need, you just recall from elsewhere. We'll just recall this one way. But then you can pick Q. This Q is arbitrary. So this is where actually encoder. Q becomes encoder eventually, okay, in the variation autoencoder. And this one is tractable. The reason is you have a new parameter to train, encoder. This guy now becomes your loss. We will see this one is tractable loss, and then the whole thing becomes tractable. Okay, so this one. The point is making intractable stuff become tractable. So you introduce a so-called variational family, another parameter, which naturally goes to the encoder. Starting from decoder P, you get encoder Q. This is a remark. So we will not go through that, but we just take this formulation. So, and we will take it for granted here, and then we will, this is not too difficult to prove, by the way. So it just, I mean, including this statement, but we will skip that in this. You just say, how do you derive? So elbow for VAE, right? First, you consider a decoder probability model. This can be a very general probability model. It doesn't have to be the Gaussian probability, but we use that for illustration, the decoder plus Gaussian noise one. And this is a general probability model. Example is the one we give. And in the homework, we give a little bit different. It's just a binary probability model. It's more like a logis model. So in the homework, coming from logis, sample from 0, 1. That's a homework, okay? Decoder probability, encoder probability model. This is now become, we started with that. This one is a joint trained. This is coming from the variational methods. You have additional trainable parameter, right? This one have a trainable parameter theta. You have additional trainable parameter. This one again for generation, this one for representation. Using variational method, this guy is what we want to do the maximum likelihood. Here we just have theta. We don't have this phi parameter. But by using the elbow, which plug that in, this is just directly copy the elbow from previous slides. So this is a KL, this is a log likelihood. This one will be the decoder loss negative because we maximize the log likelihood. Negative log likelihood will be the loss, right? So this is negative. And this is where the encoder comes in. Decoder, now we introduce encoder now here. And again, encoder becomes a distribution. So this is just, if you believe in variable, this one you can either memorize, just remember where to get it from, and then you, this is naturally coming out of the decoder, okay? So this becomes a formulation. Now we want to say what eventually it leads to, right? So this is a mathematical part, the starting point in our sense, so-called elbow, and the elbow, because this guy is a lower bound of this. You maximize this, you maximize lower bound, guarantees that this one is large. So you want to have as large as possible theta. But because this is a lower bound, you maximize the lower bound, so you guarantee if this one is large, right, lower bound, with this one is also large. So that's why it's a conservative estimate of your likelihood. You guarantee you have a good likelihood once you have this. Okay, so this is you know, there's a lot of symbols. I hope even you don't hard for you, but you hope the high level, because I try to make high level where it comes from, at least logic, hopefully it goes through. Then that's good enough, right? So basically, maximum likelihood, encoder coming from the variational methods. And this is a variational. This KLS, by the way, just goes to, this one is only encoder, right? It's actually, if you recall our earlier lecture, this one falls where this guy, encoder loss, this distribution, encoder distribution similar to PZ. PZ, what is PZ? PZ is the standard normal. So this is where it goes to similar to the standard normal. This one says reconstruction error is small. This one says similar to standard normal. So basically, this is two things get together. Elbow with a diagonal Gaussian encoder, right? Encoder, okay, so we can have an arbitrary encoder. This is a decoder, right? Encoder can be separated from decoder, as I mentioned, but it's coming from the variational family. What do we want the encoder to do? This one actually we see before. This is basically what we want to do. Consider diagonal Gaussian encoder. This one is a mean and this standard deviation, right? So basically diagonal Gaussian, the sigma, this is a vector. You have a mu, have a log sigma square, there's a vector. This is the encoder. Why we use a log sigma square, right? You think about that. There are two things good about that. First is sigma is never zero. You don't want to be zero. So it's always, also this one maps to from 0 to infinity to be negative infinity to infinity. Here it's easier to model, negative infinity to infinity. So people commonly model this guy as a log sigma square rather than sigma square itself. You could model sigma square, right, if you want. But for now, I just say the encoder gets you with unconstrained, this is negative infinity to infinity, this is also negative infinity to infinity. So it's all real number, or vectors. Actually, these are both are vectors of dimension m. Okay, so now we have these. So once we have that, what we do is we have KL, right? So if we have this encoder, remember in the earlier variational method, this is elbow, right? Elbow here is only to do with the encoder only. There's nothing to do with decoder. This one is enforced. The encoder can enforce your distribution, again, latent similar to Gaussian. So this is what we want. And KL enforce that. And this one gets to that. So basically, variational is more general. The specific formula we see before, which we say, oh, this one encourages this guy to be 0, this guy to be 1, is exactly the KL for diagonal Gaussian, which is only based on encoder. If you have an encoder of this structure, calculate KL with standard normal, this is your answer, okay? We'll try to prove that quickly, or maybe we can go a little bit quicker on that. Maybe we should go a little bit quicker, but just say this is, you can say the theorem, or you can say it's a calculation, but this is a result on its own, only to do with encoder. So once you say, oh, whatever decoder I have, I just fix this particular encoder, right? And this works. with diagonal Gaussian, elbow become this guy. This is a general likelihood, and we can plug in our likelihood to be a least square reconstruction error, but you could put a other likelihood for the generation. How do you generate X from Z? This one can be more general, but this one is this guy, okay? Yeah. So these become the elbow with this diagonal Gaussian encoder. So we only focus on diagonal Gaussian encoder because this is so simple. This easy to implement. If you say I don't want to have diagonal Gaussian, then it can be complicated. We will quickly go over this. Maybe not to. This is a Gaussian. This is a calculus. So let's say it's a calculus. I think it's a calculus 1 or calculus 2. I don't know. So, but basically, it's an integration. You have log p is while you have a KL, you have log p and log q. So basically expectation, and p is log p is this guy. It's just a Gaussian normal. P is a normal, right? Gaussian, and then we take expectation. This is a Gaussian distribution. The mean, actually, if you look at this one, this mean is mu. And standard deviation is a sigma. So if you look at the z square, you have a variance formula, which is a mean square plus your variance. Variance is sigma square. So basically what it does is the following. This guy, right, because this is a normal with a mean mu, and the sigma square is a standard deviation. So basically it's a mean square and sigma I square. So basically this is actually this form. And then plug in, you get this guy. This one is after computation, this is what you get. Okay, after computation for the Gaussian, you compute this. And similarly, so we'll go a little bit quick. You can check just doing your probability homework. This is the entropy of your Gaussian and the Q and the log Q. And then what is this guy is basically, I mean, just write down the log likelihood. This is just a log likelihood, and this one, okay. So when you integrate out that, what it is, right? Thing. This distributed according to Q. Q has a mu is your mean. Sigma square is a standard deviation, right? And then you say, okay, Z is a distributed according to Q. Z minus mu and divided by sigma square. What the integration would be if you say? It's 1. Yeah, basically after you take expectation. So taking this one, yeah, this one is coming from here. It's just 1. Okay, so you have a negative sign gets to here. So it's just 1. And then basically you put that together. This guy is these two adding. 1 is coming from 1, 1 coming from 2. Get you this. So basically this formula just by using Gaussian calculus, a simple Gaussian calculus. Yeah, either in the probability class or maybe in the probability class or in the whatever class. Right? But you just do that. Yeah, this shows that these are the KL formulation. So this I think the only thing require calculation. The other one you again it's a conceptual. I mean, hopefully you know. Although there's a lot of symbols, if you can map symbol to meaning, that will be good. Basically the meaning will be like encoder decoder, right? So in the case of decoder for the generation, that's a starting point. The probability model comes from. Encoder is introduced here as a byproduct with a variational formula. And this byproduct have a natural KL, which is enforcing this guy to be identity, to be standard normal. So that's how it works. And this is the formula. And if you combine that elbow for Gaussian decoder, we have this Gaussian decoder, right? So if you recall that given Z, X is constructed plus Gaussian noise. Tau has to be non-zero because of the reason becomes non-singular otherwise. And this is a log likelihood of your thing. And then with a diagonal Gaussian. This is what we computed. Right? The negative elbow now becomes this. So this is final our objective, and this objective is the same as what we showed before. So this one comes from the negative log likelihood coming from this guy. I just ignore the constant. And this one is a reconstruction error, but it's a reconstruction loss, right? So it's coming from this guy. And this divided by 2 eta square. Later we can multiply 2 eta square to both this guy. And then this one becomes 2 times eta square becomes eta square. And this is where we show and what we will implement. But here, this negative lot, this KL. KL is if you go back, is basically enforce your encoder distribution. All this encoder looks like standard normal. And this one gets you there. So that's about it. Yeah, so basically if you read this is encoder, and this all to do with encoder only, KL. Okay, and this guy. We still have additional trick in order to implement this. The additional trick is the following. The reason is following. So if you look at this one contains model parameter. It is okay. This guy contains model parameter, right? If you do forward, it's okay. The problem is Z contains here contains model parameter. This is a little bit tricky. The general way is if you have this something like a sampling from model parameter, you have to use policy gradient. But here, the solution is instead of a policy gradient, using so-called reparameterization, which we will talk about that. First, feed the data. You have noisy Z according to distribution. And this one, regularization output towards normal. Okay, so this is the interpretation of these two terms. Reparametrization, right? If you look at this guy, the main part is this, right? So you want to draw sample from some distribution which has a parameter. The standard way to do that is policy gradient, but here you can do a simple way. So this guy is a normal distribution with this output. What you can do is this one is sampling is somewhat difficult when you do the differentiation. What you do is doing the following. If I do this sampling, it's equivalent to this one and using this sampling. If I do this sampling, right? So this sampling, now this noisy part is has no model parameter. Model parameter doesn't come through this sampling. Model parameter coming sampling is trickier than model parameter doesn't come with sampling. So this one says the model parameter doesn't come from sampling. This one model parameter is coming from sampling distribution, right? But you just using simple Gaussian property, mean plus standard deviation times sigma times epsilon. Epsilon has no model parameter. Then it's easier. Basically, this is an easier problem considered. When you do the optimization, you just draw one set. So basically, this is called reparametrization. And we can do that with this. So here is a VAE with reparametrization. It's just a small trick, shifting the sampling Z here into the sampling of epsilon. And this one is a Z. This one is a Z, right? This is a noisy reconstruction. This one is basically reparametrization. And this is Z. This one actually what we showed earlier, also using this particular formula, right? So basically, this is the formula which we will try to use. Z, it's noisy Z. This encoder or output becomes a mean and log of sigma square. And now you use that. And here, this regularization, again, this regularization enforces your mu to be 0 and the sigma to be 1, so that it looks like a standard normal distribution. So here, and this one. Okay, so that's about it. This one is encoder. Just recall, this coming encoder, this is decoder. This one mostly decoder loss, but certainly it involves randomness from encoder because these two has encoder. So if you differentiate the loss, it will affect the encoder as well. Not only affect the decoder, but also encoder. This couples encoder and the decoder, right? This one, you want to have something like autoencoder. You have encoder, decoder coupled together. So this one, it's a generative loss, but it's affecting encoder and decoder. Yeah, this one is only affecting encoder, just making your encoded distribution like normal. Encoder trained by KL and the reconstruction here and this guy, they all back propagates. Decoder is only reconstruction, has nothing to do with term. So this one just showing how to generate. This observation noise level in the image space is some parameter you can tune in the VAE so that it trades off of your reconstruction error, how close this one should be, versus your regularization, how this one looks like normal. So basically, this one is what it actually will be the final objective function which you can implement in the VAE. We will see the implementation. But basically, this is what you implement. This one is reparametrization. So instead of draw Z, you draw epsilon. Epsilon has no model parameter. And then you do a transform, model parameter all becomes a loss, right? No, not in the sampling. Any questions so far? Hope I'm not lost, but at least you can read again. But hopefully you just map different things. Then that's good enough, right? So basically, this is decoder loss, and this one actually just the loss function we showed in the beginning when we starting to look at the VAE. If you think about it from autoencoder, this is like an autoencoder with noise. Noise is instead of a denoising autoencoder adding to the input, this one adding to the latent space Z, right? Like denoising autoencoder, but adding noise to the latent space Z. But otherwise, it's autoencoder. This one is where the latent regularization, which we say we need to do that in order to say latent has to be like standard normal. So we motivate that before, and this becomes that. So this is the final training objective, which right. How do you generate new samples after you train that, right? Think about that, yeah. Basically, the standard way to generate is you just draw Z from standard normal and pass the decoder, right? Basically, yeah. That's how you draw samples. You can add additional epsilon, like this probability model, but in reality, people don't. It's just typical example with epsilon when you really draw samples. So basically, this is what you do. I mean, you could add additional epsilon according to a probability model, as I mentioned, but you can just do in this, right? So okay, so that's about it. Let's look at what we want. I will just do a slight generalization. This slight generalization really just doesn't. At this point, we are looking at unconditional generation. Basically, conditional, unconditional. You want to say prompt. You have a conditional. If you say give a large language model nothing, ask them to free text. It's unconditional, right? You're always condition on something. So in the conditional generation, it's pretty simple. In our case, it's not too much different. It just say you want to model y given x. In here, you generate y, condition on x. X the condition, text prompt, class label, or whatever other things, and you generate y, right? So, and you only need to just say, oh, I put a condition as input to my decoder. I put a condition as encoder to my encoder. So that's the only thing you need to do. Other than that, there's nothing particularly difference by condition. Used to be you have a y to this guy that, but now here this. Again, for the variation autoencoder, this one doesn't change. It only changes the input of your encoder and the decoder. So that's fairly easy. It doesn't change much. And this loss function will be negative log likelihood loss, right? So basically, yeah. So encoder produces this guy. Encoder produces this guy, and you're sampling. this, right? So basically, your sampling, Z is mean plus standard deviation times your noise. Decoder reconstruct this guy. And now you get your final, usually this loss will be negative log likelihood. Okay, so that's a typical setting for this setup. Conditional VA with diagonal encoder. Remember, diagonal encoder, the only thing it controls is controls the reparametrization, and it controls the KL distance as a standard normal, right? So we are doing the same thing. Only thing we have additional condition on X. Y is what you want to generate now. There's shift notation. Used to be say we generate X. Now we given X generate Y, right? So we have XY, XY. So that's the only thing is changed. It doesn't change much. And here it's just a repetition of before. This is reparametrization. This is also to do with encoder. This coming the encoder. This is a decoder. This is for the generation model. The outside the P theta is decoder, and this guy mu is encoder. It's coming from here, right? And then this one is a KL of your encoder distribution similar to standard normal, so that you're guaranteed that you can draw sample from standard normal in the hidden space. So that's yeah, that's about what it looks like for the encoder, decoder. So any questions so far? This one just the same as before. We're just repeating the same. It's just putting additional condition X. So everything instead of a Y, you're adding X and a Y. So that's all. Yeah. And you can train that because you see the examples prompt and generate the image, right? For example, then you just go through this formula. You just need to say what do you want to model as prompt, what do you model as generation, and then you just do that. And it becomes part of the model. So let's look at the code. So for the code, what we have is following. So this is a VAE. Basically, if you look at the encoder, right? This is we'll see encoder decoder, but the encoder decoder is similar to before, but we will take a look at that. But anyway, so especially encoder, I mean, it's simple implementation, but we just see that make it easier. Encoder output, remember, it's a log of a sigma square, log of var. It's a log of var. Log of var is a log sigma square. Okay, so and standard deviation will be exponential of this guy, square root of that, right? So basically, that's standard deviation. Epsilon is the noise, reparametrization noise, right? So basically, it's mu times standard deviation times this guy. Okay, so that's the formula we talked about before. So reparametrize, implement the reparametrization. This one is the encoder output. Given something like whatever then you give it forward x, y. This is encoder. Encoder only depends on x, y. X is the condition, y is what it has. Yeah, so basically mu and log 1. So z is so this one is encoder. We will see how, I mean, it's implemented is simple, but then basically encoder now, the autoencoder, right, gives the mu. Variational autoencoder, in addition to mu, you also have a log of variance, log of sigma square. So this is what it gets you. And then it goes through reparametrization. So reparametrization gets you z. Z will be random. It's mu plus standard. So this is the implementation, exactly what we do. And go through decoder. This now becomes your z. Okay, z is reparametrized. Z then you go through this as a decoder. This is your forward. Forward has randomness, which is actually okay. So if you look at the forward calculation, you sample something, as long as the sampling is outside, it's kind of a stochastic gradient. You can check it's okay. Basically, sampling is actually expectation of the taking expectation over epsilon. So basically, yeah, this is fine. So this one forward get you the y. Why you want to forward get you mu and log of r, right? Think about that. So this one is your reconstruction. After that, because when you pass to the loss function, you need this one to have a KL loss. Okay. So now let's look at the loss function implementation. This is the VAE, right? VAE, you have a forward, you have a two model. One is encoder model, one is a decoder model, which they all have parameters. Two neural networks. You have a loss function. Loss function is reconstruction loss. So this one is a reconstruction loss. Okay. Y minus y hat square. You basically whatever you do. This is KL, right? This is KL. We mentioned that this is only to do with encoder. It's a bypass by forward, but this guy only come from the encoder, right? Just passing the encoder. And KL is this guy, 0.5 times, this is the formula we have seen before. It's just this guy, log of r, times mu square minus 1, which doesn't matter here, minus log of r. Log of r is, yeah, basically log sigma square, which is encoder output, which is in the formula. And expansion log r is basic sigma square, which also basically sigma square minus log sigma square. Okay, this one is a sigma square. This is a log sigma square. Okay, so this is essentially what it looks like, and you sum that. And this guy, the original loss function is a reconstruction error divided by 2 times the tau square plus KL. Now we just multiply that by this one. So this one becomes 1. This one you have 2 times tau square times KL loss. Okay. So this essentially this is where you get, and you get your loss function. After you get this loss, you do a backward, which gets you the backward optimization. So you are okay. Okay. So this is a whole training loss function computation, as well as the forward for the training process. Backward is just automatic. They're all the same. We can look a little bit about the implementation of the loss function. The encoder. The encoder is pretty simple. This one is the same as what we have done before when we look at this CNN encoder, right? You have an image. You have a class label, probably in our case, encoder. Then basically you just do this up to here. Oh, actually, this one doesn't depend on class. So this one is, I think, is optionally remove the class dependence, which is okay. But because you can do arbitrary what you want for the encoder. And this guy embedding, right? So basically, instead of this guy, you pass the dimension to 2. One you have a mu, one have a log. So they share the common embedding, and yeah, they share this common embedding, and then this embedding. Let me see. Yeah, I think this one embedding is yeah, basically they share this common embedding, and then once you embedding, you get a 2z dimension, right? Each one is for that. So basically, you could also get one linear and split that, but this one just has a 2 linear. So here is how it does. You go this. I think you go this. Basically, this is embedding of this CN step. After that, you have 2 hats. One is mu, one is log var. So that's all. So implementation pretty flexible, pretty simple. You can always you can add other things you want, but for VAE, mu and log sigma square is what you want. Add them. So implementation just small modification. For the autoencoder, you only need mu. For the VAE, you need both mu and log var. So that's you just have additional head to get that. Decoder should be the same as before. So decoder, if you look, is a deconvolution, which we talked about last time. We will not go. It's basically Z, right? And then you just look at this transposed convolution, then get Y is your image, and then you return image. So this one you don't need to change. It's the same as before. You only need to change the encoder, just have an additional head to log var, and you only need to change the VAE formulation with the reparametrization with additional KL loss. So there are a few places you have a small modification. Programming-wise, it's pretty simple, right? Just a few more lines. It's just a lot of derivation you need to be careful. So that's kind of some of the machine learning models like generative AI models like this. When you say add a program, it's just simple. It's just simple modification. It's nothing particularly sophisticated. It doesn't basically, let's say, it doesn't test your programming skill. Programming skill, if you do before 2 days, is better than how do you do that, right? The formula behind that is a part which makes the difference. So that's that's about what is this implementation, and the math is given before that. This is just an example generation. So you are generating, basically generated from standard normal, right? So it's just examples. This is the one. This one has 3 labels, just trained with 3 labels. Simple, I mean 1, 2. And this one is mixed labels. It doesn't, it's something, you can say whether it mixes or it doesn't mixes and so on. Right, so basically that's about it. So essentially, this one says it can do generation. When you start with the standard normal, is from your latent space, you use a VAE trained, it generates naturally with different labels. So this one only say labels, then you start to generate from that. If you do the autoencoder, it may not. It will not be as easy to generate. The only reason for that is whether latent space looks like standard normal. And the VA also has a nice thing about its whole process probability modeling with the approximate variational method. So it's only starting with the decoder, starting with the probability model from latent space to your generation. But then it actually introduces encoder, and so that introduce variational method and so on. So and you introduce simplification so that it's trainable. I will give a final one. I think that's about it. And some part is a little bit more math, but you have to read that to hopefully understand the high level. But here is general. I just read that. This is for reference. We don't want, because sometimes you may want something more. This is for Gaussian elbow, right? Think about the VAE. You start with a probability model, right? This guy with a likelihood. This is conditional. Just make it a conditional. Z is your latent space. It's a original thinking about the standard normal. Now in this case, we say, what if I do not standard normal? I know mu 0, sigma 0, right? So I mean, this is just arbitrary. Just say, assuming if that's what you want to do, then you can still have the formulation, and assuming you also have a general Gaussian variational family, right? Instead of in the VAE, the practical solution is a diagonal. This one is the same. Here, in the practical way, is a diagonal, right? We have a diagonal. Here, just assuming instead of diagonal, let's say full covariant matrix or structured covariant matrix, whatever it is. But basically it says, okay, if you have this is beyond standard normal, it's just a general Gaussian. This one is also general Gaussian with especially this covariance matrix, which is relatively more costly rather than mean. Right? Mean is always the same dimension. Then what do you do, right? So this one is encoder. This one we could also model log sigma. For now, it just make a sigma. It's just for simplicity. But you could model log of sigma and then use exponential and so on. And here is basically what it is. This becomes reparametrization. This is a general reparametrization with a general covariance, right? And this one is the KL between this guy and this guy. Basically, there's a general formulation for general. You can search on the probably Wikipedia, whatever. Just look at the KL, and this one is about what it looks like. Okay, the KL between two Gaussian distributions. So the final formulation in the will be Gaussian. Of course, it can be computational expensive for full covariance. So that's why in our implementation, we always use diagonal. Okay, so that's all. Yeah, so this is based on this paper, classical paper, and this is a very well-known influential paper. And anyway, hopefully you understand the motivations and the high-level concepts. So we're done.